Okay, today we're talking about Chapter 4, Section 5, Exponential Growth and Decay, Modeling Data. Now, I know that word problems is a source of anxiety for many students, but the thing is, like with everything in life that you might have some sort of anxiety about, the best way to go at it is to just really go at it. Now, these word problems, and all of them, especially in this course, they are pretty. I want to say linear in terms of the thinking is pretty straightforward. Now there will be problems if you do go to calculus and things like that, where you have to think your way through the problem. A lot of them require use of Pythagorean theorem, things like that. But for this course, a lot of the word problems are just they're pretty straightforward. And you'll see that in today's section, and I'll go ahead and give you the spiel about how when I was in school, I would see these word problems, and again like I've told you before with piecewise functions, where I'd see piecewise functions and I would just be like, nope, hope there's not a lot of those on the test and be done with it. I was the same way with word problems. Now of course this got me into a lot of trouble, and I hope that you avoid the same trouble that I did. That's really about it. There's no guarantee, but they are pretty simple once you do them, especially once you do a couple of them. And I don't think you should take the same path I did and say, no, we're not doing that. Okay, so let's just look at this. Oh shoot, I totally forgot to talk about this. I'm sorry. Okay, so exponential growth and decay models. The mathematical model for exponential growth or decay is given by, and we have the functions f of t is equal to a, and that's a sub-zero, right? We say a naught. That just, well, that tells us here in a minute, I think. All right, well, it means the initial amount, okay? Times e raised to the kt power, or a is equal to a naught times e to the kt power. So the only difference here is f of t and a. All right, they're essentially the same thing. The function at t is the amount that you get, and that's what the a is. And a naught is the initial amount. Of course, we'll see problems of the ideas of initial amounts here in a moment. All right, if k is greater than 0, the function models the amount of size as a growing entity, right? So if k is a positive number, we're increasing. If k is less than 0 or a negative number, we're decreasing. And of course, if we're increasing, we call that exponential growth. If we're decreasing, we call that exponential decay. Now, the value k, that's just going to be some constant, okay? And well, in most of these equations, you are going to have to find what k is, and of course it's simple arithmetic to get k, because if we look at this, we have 1, 2, 3. Well, that's not circling the k, and then 4, which is the t. Okay, a naught, k, and t. Right, and again, recall that e is not a variable. Okay, so we have 4 unknowns, and I've told you before that if you have n amount of unknowns, that in order for you to solve it with just one equation, you need n minus 1 of the variables, right? So if we have 4 unknowns, in order to solve it, we need to have 3 of them. So most of the time, at least, well, yeah, most of the time, in this section anyways, k is the one we're going to be finding. Okay, and we'll see that with example 1. So example 1 reads, the graph in figure 4.22, so let's go ahead and snip that. I forgot to snip 422. Here we go. Alright, so the graph in figure 422 shows the U.S. population in millions for 6 selected years. And from 1970, for 6 selected years, from 1970 through 2020. In 1970, the U.S. population was 203.3 million. By 2020, it had grown to 331 million. Find an exponential growth function that models the data for 1970 through 2020. By which year will the U.S. population reach 400 million? So we have to create an equation. Okay, so let's go ahead and create this equation. So we know that our exponential growth or decay equation is a is equal to a naught times e raised to the kt power. Okay. Now again, the k is the one we're going to is the unknown variable, unless we are just given that, right? That is the growth or decay rate. Now in this particular case, it's going to be growth because the population in the United States is growing. So let's go ahead and write down what our variables are. Again, it's a. We have a naught. Again, e is not a variable. It is a constant. The constant of the natural log, 2.71828, and then k, and then t. Okay, so from the example, we are given this data. What is the initial amount? The initial, right? That's what A naught is. What is the initial amount of people in the United States? All right. Well, in 1970, the initial amount was 203 million. So we're going to put 203.3. Alrighty. And in 2020, how many did we have? We had 331 million. And let's see, yeah, no decimal, 331 million. All right, K, well, again, that's the growth constant. We don't really know what K is, but that's okay, because that's what we're going to find. And then T, all right, well, from the initial time to the present time, well, the present in this particular example, from 1970 to 2020 was 50 years. So we're gonna say 50 for T. Now again, for A, we're not finding the growth rate. We're not finding anything. We have to derive a function first. In order to derive this function, we have to create it. So the creation of this function is going to be this process, and let's differentiate here. So we're going to we're just going to follow along with the equation in yellow by plugging in the values in white. So we have 331 is equal to 203.3 times E. I didn't really plan that one through, did I? Let's move this right up here. That's fine. Yeah, that's fine. Perfect. Where are we at? Times E to the KT power. Now we don't know what K is, but we do know T is 50 times 50. Oh, shoot. All right. So all we have to do here is figure out this particular problem. So the first thing we're going to do is we are going to we have to solve for K. So we're going to have to divide both sides by 203.3. So we're going to have 331 divided by 203.3, and that's going to be equal to E to the, let's just write 50K. All right. Well, how do we solve this problem? Well, if you recall, we have to take the natural logs of both sides, right? So we're going to take the natural log of the left side and take the natural log of the right side. So we're going to do the natural log of 331 over 203.3. That's equal to the natural log of E to the 50K. Right now, obviously, we're out of space, so let's go ahead and create that space. Like so. All right. Well, the left side, we're just going to leave it the way it is. All right. It's just going to be a natural log of 331 over 203. I mean, I know that is some number. I know that is some value. Well, the right side, though, the natural log of E, right? We know that from the previous sections that we can just put this out front, right? Because it's the exponent, and then the natural log of E is just 1. So what happens here is we're just going to end up with, the left side is natural log of 331 over 203.3. And that is equal to 50K. All right, and then we're going to divide both sides by 50. So let's go ahead and just put K on the left side here. So K is going to be equal to the natural log of 331 over 203.3, and all that over 50. Now, there can be some user error when doing this, when putting this into your calculator, but hopefully we'll avoid that. So what I like to do is I like to be very liberal with my parentheses. So I'm going to put a natural log. Well, I'm going to put parentheses to denote my numerator, parentheses, and then natural log of 331 divided by 203.3, close parentheses, and then divided by parentheses 50. So I'm going to get approximately 0.0, and it's 0.97. So we're just going to go to 0.01. So K is 0.01. So this tells me that my equation now, my equation is going to be A is equal to, again, the A naught is still going to be there, which is 203.3 times E, now to the KT power, which is 0.01 T. That is my equation I'm going to use to solve B. So let's go ahead and snip this, put us on a new page, as well as we're going to re-snip the problem so we know exactly what we're doing here, what we're using this equation for. Okay. So this B reads, by which year will the U.S. population reach 400 million? So we want to know when the A over here on the left side is going to reach 400 million. Now looking at the equation that we got, we have one unknown and we have two unknowns. So we have two unknowns. One, the A is, the population, and T is the amount of time. Or we're wanting to know by which amount of time will we reach 400 million. So what we have to do here is we have to substitute 400 in for A. So this is B. So we're going to put 400 in for A, 203.3 times E to the 0.01 T power. Now we have to do our arithmetic here, and we have to solve for T. Okay, so doing this, kind of similar to what we did before, we're going to have to divide both sides with 203.3, so we're going to have a 400 divided by 203.3, and that's going to be equal to e raised to the 0.01 t power. We're going to take the natural log of both sides, so let's go ahead and move this over a little bit. Move this over a little bit. So we're going to take the natural logs of both sides. So we're going to end up with the natural log of 400 over 203.3 divided, or I'm sorry, is equal to 0.01 t. So I need to divide both sides with 0.01. So let's go ahead and let's solve for t over here. So t, and then move my toolbar. It's a little bit in the way. There we go. So we're going to have t is equal to, this is going to get a little tricky, so let's change colors here so they don't run together. No, yeah, no, okay, yeah, that's okay. So t is equal to the natural log of 400 divided by 203.3 divided by 0.01. And so that means, if we do this arithmetic right, we've got the natural log of 400 divided by 203.3, and then that is going to be divided by 0.01, so we have 67.67. We'll put the approximate symbol here. Again, approximately, so equal sign is, well, usually straight lines. The approximate is like 2 tildes, or tildes, I don't know, 68. So 68 years after 1970, so this means 68 years of 1970, that puts us at 2038. So in the year 2038, using the growth model, we can expect to have a population of 400 million people in the United States in 2038. So that is, we're 15 minutes in, and that is example 1. Again, look, I know word problems, source of anxiety, all that good stuff. But it's just, if you just tackle it, and you just kind of think your way through it, especially, kind of follow along with what I'm doing here, then you should be okay. All right, so example 2, we're going to be talking about the Dead Sea Scrolls. So I think this is an example that is in every single one of the textbooks I've ever taught out of. So use the fact that after 5,715 years, a given amount of carbon-14 would be decaying. So real quick, let's go ahead and put our equation up here to kind of follow along with it. A naught times e to the kt power. Real quickly, let me. There was something that I did like about this textbook that I forgot to put. Okay, so we're gonna put that next to the. Hang tight. Put it right here. I thought this was interesting. To be honest with you, I always think about this, but I never put it down because there's just everybody thinks differently. But this reads, why does the formula for exponential growth look familiar? Well, I mean, it looks familiar because it is in the similar vein as A is equal to PERT, right? I mean, PE to the RT, then we have A naught, which is the same thing as principal, and then the R and K. Well, R is interest rate, and R is interest rate, and K is the growth rate. So they do have a similar pattern here because they are similar. Of course, I think this is definitely one of the easier equations to memorize, but I think it's given to you in every problem. But I mean, it's not going to hurt you to give that a little memorization, anyways. So this reads, use the fact. Now we have to do a little bit of finesse here. All right, a little bit of thinking outside the box. Use the fact that after 5,715 years, a given amount of carbon-14 will have decayed to half the original amount. Okay, so what exactly are we going to do with that information? Well, I would half the original amount to find the exponential decay model for carbon-14. That's all we're given for A, right? We're trying to find, again, we're looking for the exponential decay, so we're going to be looking for, the unknown here is going to be the K, okay? 5,715 years, well, that is our T, but we don't really have the A and the A naught. So let's go and write this out like we did in example 1. We have the A naught, K, and the T. Okay. Well, again, the T is pretty simple. It's 5,715 years. 5,715. And then we have K. That's going to be our unknown. That's what we're looking for. Did I put a question mark there? No, I just left the blank because we didn't know. Okay, good. Okay. So A and A naught. We don't really have hard and fast numbers like we did in example 1, but we have to just kind of think about this, right? So going back to the problem, it reads, use the fact that after 5,715 years, a given amount of carbon-14 will have decayed to half the original amount. Okay, well, how much was the original amount? We don't know, but we do know that the original amount was the original amount. Okay, now follow me here. If I were to say, and this is just really Sheldon from Big Bang Theory kind of way to say it, if I were to say Kroger is 5 miles away, well that's nice hard fast numbers that we're used to. All right, well, if somebody says, Sherman, how far away is Kroger, and I don't know the exact amount, I would say Kroger is the distance away from us that Kroger is. Really stupid way to say it, doesn't it? It's kind of stupid, but but you'll see where it ties in. Okay, so we don't have the actual original amount, A naught, but let's read further. After 5,715 years, a given amount of carbon-14 data will have decayed to half the original amount, and again, the original amount is the original amount, and the amount now is half of the original amount. And this is where it gets a little confusing, but a little clever. The amount now is half the original amount. The original amount, well, was original amount. We don't know the original amount, but in this particular case, it doesn't matter, and you'll see why here. So let's tie all this together. And for the record, This is how you do every single one of these Dead Sea Scroll problems. So if you're like, well, how, you know, I might not think about that. Like, you see Dead Sea Scrolls, you're going to do this, okay? Anyways, so now we're going to actually plug these values into the equation in yellow. So we're going to have A, well, A is A naught divided by 2. That's going to be equal to, well, A naught is A naught. And then times E to the KT power. So let's just go ahead and write 5715K. Okay, so now we have to solve for K, right? Well, the first thing we need to do is get K by itself, and so we need to divide both sides by A naught. And here's where the cleverness comes into play. If we divide both sides by A naught, right, so this is going to be A, well, let's put a different color, let's make it red. Put it A naught divided by 2, and then we divide both sides by A naught. My toolbar. We divide both sides by A naught, right? This is what happens when we divide both sides by A naught. And real quickly, well, let me finish this out, okay? This ends up being just simply 1/2, okay? And if you forgot how that is, why that is, I mean, I do this in my head where I put the denominator, oops, where I move the denominator of the numerator to the denominator of the denominator, and then of course we have the fraction. But let's say that you don't have the experience that I do dividing fractions. You know that it essentially looks like this, right? If I divide both sides by A naught, I also know that what I can do here is I can replace this division sign, replace this division sign, and I multiply by the reciprocal. So instead of A naught, I say 1 over A naught. And now this becomes A naught over 2 times A naught. The A naughts cancel, and we have 1/2, like I mentioned earlier. So that's why, it's not necessarily imperative that we know what A naught is, because, well, we can do something really clever and just kind of cancel it out with the amount now. And again, this is how you're going to do every single Dead Sea Scroll problem, I think. Anyways, I've come across not doing it like this. So anyways, we have 1/2 is equal to E times 5715 times K. I'm going to take the natural log of both sides. So once again, let's move this to the right just a little bit. Let's move this to the right just a little bit. Got to make space for the natural log. Okay. So this becomes, I'm just going to flip both sides again because I like having my variable, my unknown on the left. So we're going to have K is equal to, well, not K, sorry, jumped ahead of myself. 5,715K is going to be equal to the natural log of 1/2. Okay. So let's go ahead and snip this to the next page. Let's snip it better than that. Okay, and then if we solve for K, we end up with, let's put this in. All right, cheated a little bit there. Had it ready. K is equal to a negative 0.30. 0.000121. Okay, so that's what K is equal to. So now this means that my equation for my decay model for these for the Dead Sea Scrolls is going to be A is equal to some A naught times e to the KT power. Well, K is a negative 0.000121 times T. Now let's go back and get what B is asking for. Ooh, that's so example 1. Oh yeah, I went back and looked at the one thing. Okay. So this is my equation. Alright, so now we can proceed to B. We have our equation, we can proceed. So in 1947, the Dead Sea Scrolls contained 94. Earthenware jars containing what are known as the Dead Sea Scrolls were found by the Arab Bedouin herdsmen. By an Arab Bedouin herdsman. Analysis indicates that the scroll wrappings contain 76% of their original carbon-14. Estimate the age of the Dead Sea Scrolls. Okay, so 76% of the original amount. Again, we don't know what the original amount is, but that's okay. We can just do something clever. Well, how would I write 76% of the original amount? Well, I would write 0.76 A naught. That is 76% of the original amount. And that is the hard part for this particular problem. That is it. And of course, that is equal to A naught times e to the negative 0.000121 t. Okay, and then I'm gonna try and I'm gonna put this all on one page. So I'm just gonna show you the nice clean part of the computation. This is computation we've done before. There's nothing new. The hard part here was well, I don't need to do that. The hard part here was setting the problem up, and we set it up. So looking at this particular problem, let's make it a little bit larger at least. So notice how we set the problem up. We said 0.76 of A naught, and then when you divide both sides by A naught, the A naughts disappear. We end up with 0.76 times e to that ridiculous number. Take natural logs of both sides like we have been doing, solve for t, and we see that the Dead Sea Scrolls, the estimated age of them was 2,268 years old. Okay, and so if they were discovered in 1947 and then they were 2,268 years old, let's see, we can do that math real quick. Probably do it in our head, but so they were probably written about 321 BC. So that's interesting. So again, that's how you're going to do the Dead Sea Scroll problems. Alrighty, so the logistic growth model. So we just looked at the exponential growth model. Now we're going to look at the logistic growth model. Now, the exponential growth model, as cool as it is, has its limitations. I mean, the logistic growth model does too, but the exponential growth model has its limitations, and here's why. Let's just examine this. Let's go back to one of the problems right here. As a matter of fact, let me go ahead and put this into a graphing calculator and kind of tell you how this can get really ridiculous. So give me 1 second. We have two. Okay, so Desmos graphing calculator. So my equation was 203.3 times e raised to the 0.01 and t power. Okay. Okay, so you can't see this obviously, but I'm looking at and of course you could follow along with this if you put this into your calculator, and you're just gonna take my word for it. Or yeah, you just have to take my word for it. So we have what I'm looking at here. Let's go to, all right, we're going back to example one. Example one having the U.S. population. Okay, so we know that it is an exponential equation. Now the problem with exponential equations is that they go up exponentially. All right, and let's just say 1,000. Okay, so, ooh, that's a crazy number. Oh, that is beyond crazy actually. We actually don't. Let me see. All right, hang tight. You might want to fast forward it for the next 40, 50 seconds maybe while I scroll up here. Holy cow. Now, obviously, the world population has, pretty much exploded since, you know, like the medieval ages, right? You know, we'll just go to 900. Actually, it won't let me click 900. All right, 831. Okay, so yeah, we can maybe get to 900. Whatever. All right, so how would I do this? So according to the exponential growth model, about 800 years after 1972, this will be what, 2672, right? So about 800 years, and so in 2672, which is a long ways away, don't get me wrong, the population of the United States should be, that doesn't sound too absurd, should be about 805 million. Okay, the thing is, that's a lot of people. And the problem with exponential growth models is that they grow. You know, let's do it this way. We have a petri dish. Okay, we have a petri dish with a bunch of little bacteria. Right. Well, we have a little petri dish, and we have a function that models the growth of these bacteria. Okay. And for the sake of it, let's just say they're giant bacteria, you know, because I mean, I'm pretty sure there's thousands or millions of bacteria, but let's just say they're really small. You start off with 10 bacteria, and in a month, if you were to follow along with an exponential equation, you might say that there are, you know, 300 trillion bacteria. Well, the thing is, the petri dish is so small, the food is limited, that in a month you cannot have 300 trillion bacteria. That is a literal impossibility. And I'm not even sure if this helps, but that's a limiting factor of exponential equations. Is they're very limited in terms of what model you can model, essentially, because things do not always grow exponentially. There will not always be unlimited space and unlimited food, and that's a good way to put it. And I'll stop there because I feel like I've rambled for the past 5 minutes. But anyways, logistic growth. So in comes logistic growth. Logistic growth tells us that, okay, something can grow. Look here. Something can grow, but at some point we have to level off, right? We cannot just grow and grow forever because there's limited space, there's limited food, there's limited supplies, there's limited everything. Okay, and that's what the logistic growth model is. Now, looking at the definition, the mathematical model for limited logistic growth is given by this equation here. And again, same as before with the exponential growth, f of t and a, they're essentially, you know, interchangeable because, you know, a is the amount, f of t is that amount after t time. So a, b, and c are constants with c greater than 0 and b greater than 0. Now, I don't know if it necessarily says, it doesn't say it here, but this c is called what's called the carrying capacity. And it's basically the tippy top that we can get to. And we'll discuss that more here in a moment. Okay. So this is pretty quick. This book came out really fast with coronavirus equations. So let's go ahead and snip all this just for sake of time. I feel like I've rambled quite a bit. Well, maybe I shouldn't have. Yeah, this will be fine. I mean, all it is at this point is plug and chug. So we'll put this over here. So I've heard, and you probably heard too, but the average attention span of somebody is 10 minutes, and so all these videos obviously go over 10 minutes. So I try to streamline these problems a little bit more, but obviously, you know, you can pause and do whatever you want to in between. But for this problem, I think it might be best if I just did this. So looking at example 3, in the figure 3.11 repeated from chapter 3 shows the number of new coronavirus cases in the United States for 7 selected days in 2020. And this is for March. Okay, March 14th, 24th. These are just randomly selected days. So the function that we see here models the number of new coronavirus cases in the United States. F of t, again, which would just be the amount. So let's go ahead and put that as the amount here. Okay, that's the same thing as saying the amount. T days after March 14th, pi day. Okay. So use the model to determine the number of new coronavirus cases on March 14th. So how do we know how many coronavirus cases we have on March 14th? Well, how many days after March 14th is March 14th? Well, that's pretty easy. It's 0 days after March 14th, and that's all you do. You just plug in 0 for t. And we can well, I say kind of. We can kind of do most of this in our head. So if we plug in a 0 right here for t, well, I mean, 0 times anything is 0, so it doesn't matter what the k value there is. And then e to the 0th power, anything to the 0th power is 1, so 62 times 1 is 62, plus 1 is 63. So we end up with the equation right here, 26,462 divided by essentially 63, right? And so we get 420. So according to the model, there are approximately 420 new coronavirus cases on March 14th, and that's just the initial amount. Okay. B, we need to use the model to determine the number of new coronavirus cases on March 24th. Okay. Well, and of course it asks, does it overestimate or underestimate the actual number shown on the bar graph? So this is an actual number. This is the actual number of cases, and we just have a model number. Okay. And so March 24th is 10 days after March 14th, so we're just going to plug in a 10 for t. So we're going to plug in a 10 for t, and we end up with the number 20,208. Now on March 24th, we have 20,304. So it underestimates the amount by about 133 cases. But I mean, it's still pretty darn accurate, right? I mean, we're trying to model the future here, and that's essentially how the whole, flatten the curve and all that stuff is. It doesn't really matter what your political opinion is. Data like this was modeled to determine, what we should do as a country and as a world, what we should do. So anyways, C reads, according to the model, what is the limiting size? So here's the cool thing about this about C. I said before in this equation, the top number is what's called the carrying capacity. That's just the maximum amount of number you can have. Well, according to the model, what's the limiting size? Well, it's just 26,462, and that's it. So that was pretty easy. So I think the next couple examples are pretty easy, and we can kind of scoot along. Again, I know that some of these lectures go a little bit long, but I do encourage you to put speed at 1.5 maybe, because I do ramble. And of course, if you miss something, hit rewind. But anyways, so modeling data. Throughout this chapter, we have been working primarily with models that were given. However, we can create functions that model data. So now we're going to create functions. Okay. So real quickly. If we were to see, and this is just data. They're tiny little dots. Let's see if I can't make this a little bit larger, or maybe a lot bit larger. Let's just cover this whole page. How about that? Yeah. Now it's pretty easy to see that we have all these little dots. Okay. Now these little dots are data points, and according to the data points, you can kind of see. Okay, are we growing exponentially? Are we decaying exponentially? Are we growing logarithmically? Or are we decaying logarithmically? And of course, the simple one, are we growing linearly in a straight line, right? We're not having a slight curve like we do here. Or are we declining linearly, again, in a straight line, not in a slight curve like right here. And so we're going to use this idea for the for creating modeled data. Okay, so we're going to model some data ourselves here. Maybe not in this problem, I guess. So like I said, at least two of these examples are pretty darn quick. Let's just go ahead and put them both on here. Okay, so example 4, let's look at example 4 real quick. The data in table 4.6 indicates that between the ages 1 and 11, the human brain does not grow linearly or steadily. A scatter plot for the data is shown. What type of function would be a good choice for the modeling data? Well, I mean, obviously it's not exponential because we're not going up. It's not. It's definitely not declining, and in no way does this look like it is declining. This one's declining, this one's declining, and this one's declining. Of course, we know that, right? Because we read graphs from left to right. So, what type of function would be a good choice? Well, our choices are linear, which would look something like, something like this. Whoop, wrong button. Would look something like, you know, this. Did I say linear? I meant exponential, if I did say linear. That's exponential in red. Linear would just be a nice straight line. And then, of course, this one, you know, kind of goes up, and then it looks like it kind of rounds off. So obviously, I say obviously, I don't know. So it appears that we would suggest a logarithmic function for this data set. Now, example 5, looking right at this, you would say, okay, so we have the world population. Suggest 2 types of functions that would be a good choice for modeling data. So looking at this, excuse me, looking at this particular equation, you might think that a linear model might be good. Okay, you might also think that an exponential model might be good, and you'd be right in both cases. Now, real quickly, the first thing I would probably look at is, or probably think, is that it's linear because it looks like a nice straight line, right? Now, it kind of is, but I mean, a nice straight line would have you know, the same slope. Now let's look at this over here. Let's actually look at the numbers here. All right. From 1950 to 1960, we go up 4/10. From 1960 to 1970, we go up 7/10. Right? If it was linear, we'd be going up 4/10 all the way up. But we don't see that. We actually see that it's growing a little bit differently. Right? We went up 4/10, 7/10, 8/10, 8/10, 8/10, 8/10, and then 6/10. So we're kind of growing a little bit fast, and we kind of straighten out, and then we kind of grow fast again. And so, and we could use a linear equation or an exponential equation, depending on, you know, what we want. But we know that we cannot use a logarithmic equation. All right, so that's calculator work. All right, so this is expressing an exponential model in base E. So this particular equation is shown in equivalence. Let's go ahead and put the problem here too. I think that'll be fine. There we go. All right, so we see that, and this is just an exponential equation. Y is equal to sum A, right? That's just a constant, and then B raised to X power. That's just exponential. All right, that's equivalent to saying Y is equal to A times E raised to the natural log of that B times the X. So basically, what we're doing is you know, the A is staying put, and then we're multiplying the A by E, and then we're raising the E to the natural log of what the B is. And that's really it. Just you know, can you just rearrange it? And you know, there's a lot of stuff in this section where it's not necessarily, you know, computation heavy. It's basically rearranging, and that's what we're doing here. It's just rearranging. So example 7 reads: we've seen the function g of x equal to 2.634 times 1.016 raised to x power models world population. X years after 1949. Rewrite the model in terms of base E. So in terms of base E, let's go ahead and rewrite this problem or this equation real quick. Okay, so we know that this is essentially Y. This is essentially A, this is essentially B, and of course this up here is X. So if I were to rewrite this equation in terms of base E, well, I would keep the Y, right? The Y is still g of x. The A is still the same, but we're multiplying A times E, and we're raising it to the natural log of my B. So we're going to raise this to the natural log of my B, which is 1.016, and then times x. And that's it. That's example 7. That is rewriting an exponential model in base E. And that concludes today's lecture.